Okay, welcome back. We are now going to start part 2 of our stoichiometry discussion. We are going to begin this session with example number 5 from your notes. So, as you recall from last time, stoichiometry is the mathematics of a balanced equation, so you'll notice that each time we do a stoichiometry problem, we are going to have a balanced equation to work with. Now sometimes in the question, the equation is written out in words, and so you're going to have to write the formulas for the reactants and products before you can balance them. So let's take a look at example number 5. What mass of oxygen is required to react with 100.0 grams of iron to produce iron 3 oxide? So let's write the equation. We have oxygen. Elemental oxygen is O2. And we're reacting it with iron. Iron elemental is Fe. And that's going to react to form iron 3 oxide. So let's just quickly have a review on formula writing. Iron 3 means we have iron 3 plus. It does not mean we have 3 iron atoms. That Roman numeral 3 is the charge or the oxidation number of iron. Oxide comes from oxygen, which is in group 16. And we have a 2 negative charge for those. So we have 3 positive and 2 negative. They have the number 6 in common, so Fe2 gets me to 6 positive, O3 gets me to 6 negatives. Now this is not balanced, so I'm going to put a 2 here. That gives me 6 oxygens. So I'll have a 3 on the reactant side for oxygens, and a 4 in front of the iron for my 4 iron. So I have a balanced equation. We begin with grams of iron, which we need to get to moles, because recall the coefficients in the balanced equation represent the mole ratio. So we have to get into moles. So 100.0 grams of iron, and we will go from grams of iron to moles of iron. 1 mole of iron has an atomic mass of 55.85 grams. Okay, grams of iron will divide out, and we will have the number of moles of iron involved in my reaction. So we'll pull out our calculators at this point, and let's see what we end up with here. 100.0 divided by 55.85 gives me, to 4 significant figures, 1.791 moles of iron that are reacting. So, we now need to convert moles of the given substance into moles of the unknown substance. So, 1.791 moles of iron. We are going to go from moles of iron into moles of the unknown substance, which is what mass of oxygen. That's what we're after. How much oxygen is required. So we'll go to moles of oxygen. So we will use the coefficients from the balanced equation. For every 4 irons, we need 3 moles of oxygen. Moles of iron will divide out here. So I'll have my answer from the previous problem. We will multiply by 3. And then divide that by 4, and we get 1.343 moles of oxygen will be required to react with my iron. Now we're not quite finished, because I want to know what mass of oxygen is required. So finally, I will take my 1.343 moles of oxygen. We will divide out of moles of oxygen and get into grams of oxygen. 1 mole of oxygen has a mass of 32.00 grams. So we'll pull our calculator out one more time, and we'll take our previous answer, and we will multiply that by 32.00. Whoops. And I end up with, to 4 significant figures, 42.97 grams of oxygen will be required to react with my 100 grams of iron. Now, we can do that in one expression, as I showed you on a previous problem. And this is generally speaking how we will do it from now on. We won't break it up into separate steps. We're going to do it in one expression. So we'll begin with what we know, which is my 100.0 grams of iron. And we will go from grams of iron to moles of iron. 1 mole of iron, of course, as we said earlier, 55.85 grams. Then we will go from moles of iron to moles of what we're after, which is oxygen. And as we said earlier, that's a 4 to 3 ratio from iron to oxygen, which we got from the balanced equation. And then finally, moles of oxygen to grams of oxygen. 1 mole of oxygen is 32.00 grams. So, let's do that with our calculator here. Try to get it all in view. We have 100.0 divided by 55.85 times 3 divided by 4 times 32.00. Once again, we round off to the 4 significant figures which we're allowed. We end up with 42.97 grams of oxygen. Of course, that's the same as the answer we got earlier. Now, standard procedure for stoichiometry problems when we are dealing with masses is going from grams to moles, and that's moles of what you're given. Then we're going to go from moles to moles of what we're after, and then finally we'll go from moles of what we're after to grams. So grams to moles, moles to moles, moles to grams. And we do that over and over again. If you can understand that concept, you can do just about any stoichiometry problem. So let's use that and move on to example number 6. So we want to know how many grams of oxygen are needed to burn 30.5 grams of propane. The formula for propane is given, C3H8. The products of the reaction are CO2 and water. This is a typical combustion reaction. So the equation, C3H8 and oxygen react to form CO2 and water. So let's go ahead and balance this. We need 3 carbons on this side, so I'll put a 3 in front of my CO2. We need 8 hydrogens, so I'll put a 4 in front of my water to give me 8 hydrogens. Now we need to balance our oxygens. We have 6 from the CO2, plus 4 more from the water gives me a total of 10. So if I put a 5 in front of the O2 on the reactant side, that equation's balanced. It's a 1 to 5 to 3 to 4 ratio. Now you'll notice we're just going to do this in one expression as opposed to breaking it up into separate steps as we've done in the previous examples. So we begin with what we know, 30.5 grams of propane, C3H8. We'll go from grams of propane to moles of propane. 1 mole of propane has a mass of, let's see, carbon is 12.01, and there are 3 of them. And then we will add to that the mass of 8 hydrogens, so I'll use my parentheses key, 8 times 1.01 for each hydrogen, and that gives me a mass of 44.08 grams per mole. So I now have moles of what I was given. So we're going to go from moles of what's given to moles of what I'm after, which is how many grams of oxygen do I need? So we're going to go to moles of oxygen. And the mole ratio is 1 mole of C3H8 requires 5 moles of oxygen. Once again, this comes from the coefficients in the balanced equation. 1 propane to 5 oxygens. And then finally, we will go from moles of oxygen to grams. 1 mole of oxygen has a mass of 32.00 grams. So, let's see what we get here. We have 30.5. Let's clear that actually. 30.5 divided by 44.08 times 5. We don't need to divide by 1. And then times 32.00. My calculator says 110.708. I'm only allowed, let's see, 3 significant figures here, 4 there, and 4 here. I'm allowed 3 significant figures, so we are going to round that off to 111 grams of oxygen. Okay? Now, I've added a little bit to this problem just to show you that we can actually do more than grams to moles, moles to moles, and moles to grams. The second part of this question says, how many grams of air would be needed to burn the same amount of propane? Air is 20.7% by mass oxygen. Well, let's see. Let's take our answer from the previous problem, 111 grams of oxygen. And I'm going to make up a conversion factor here that expresses the percentage of oxygen in air. I'm going to go from grams of oxygen to grams of air. Now, isn't it true, if air is 20.7% by mass oxygen, that if I had 100 grams of air, wouldn't 20.7 grams of it be oxygen? Right? That's 20.7%. So, I've used a conversion factor to go from grams of oxygen to grams of air. So, we will take our answer from the previous problem and divide it by 20.7 and multiply by 100. So, divided by 20.7 times 100, and I get to 3 significant figures, 535 grams of air would be required to complete that reaction. Alrighty, well, that wraps up our stoichiometry discussion, part 2. In class, we'll be working a few problems in small groups, and then we will apply this by doing a lab where we will react sodium bicarbonate with hydrochloric acid to make some sodium chloride, table salt. And we'll be doing that in the upcoming lecture and classes. Thank you.